So let's think of a situation where we can put into practice several of the identities that we've learned so far in this unit of study. So I want you to picture rolling a solid sphere down a ramp of height h. At the top of the ramp, the solid sphere would have gravitational potential energy, and then as it reaches the bottom of the ramp, now it's going to roll with some final angular speed, and of course along the way it develops some linear velocity as well. At any given point, a fraction of the way down the incline, it has two forms of kinetic energy, translational and rotational, and by the time it gets to the very bottom, all of the gravitational potential energy has been spent and converted into the sum of translational and rotational kinetic energy. And what I'd like to do is use what we know about rotational motion to determine what's the value of v, what's the linear speed in meters per second for this solid sphere when it reaches the bottom of the ramp. So all we have to do is identify point A and point B and recognize that mechanical energy is conserved, especially if the ball rolls without slipping. So we're not imagining a case where the solid sphere slides and rubs against the surface. Instead, as it rolls, the point of contact slightly changes as it moves along, but whatever the given point of contact is, that point of contact does not have relative motion with the surface. There's no rubbing, there's a rolling that takes place. And in that case, there's no kinetic coefficient of friction. The wheel grips the ramp with static friction, but static friction never contributes to the development of wasted thermal energy. So, conservation of mechanical energy says that the loss of gravitational potential energy results in the increase in both the translational and rotational kinetic energy for our solid sphere. mgh equals 1/2 mv squared plus 1/2 I omega squared. mgh is equal to 1/2 mv squared plus 1/2. Now we know what I is for a solid sphere. I hope you remember that that's 2/5 mr squared. And you know we can substitute omega with v over r. R gets squared and cancels. 1/2 and 2/5 gives us 1/5. So we have, now that we can cancel the m that appears in every term, is an expression that says GH is equal to 1/2 plus 1/5. And see, we're just factoring out the v squared. 1/2 plus 1/5 is the same as 5/10 plus 2/10, which gives us 7/10. So if GH is 7/10 of v squared, then v squared is 10/7 of GH. So the velocity at the bottom of the ramp is the square root of 10/7 GH. Not so bad. But wait a minute. How did we know this was a solid sphere? I guess it was just stated, but maybe we try again with a hollow sphere. Well, step 1 is still the same. Step 2 is still the same. The only difference is we wouldn't substitute 2/5 mr squared. We'd substitute 2/3 mr squared if it was a hollow sphere. So let's see what that would give us. We would have mgh equals 1/2 mv squared. That's the translational kinetic energy, plus 1/2 I omega squared. In place of I, we'll say 2/3 mr squared, and in place of omega, we'll say v over r. Okay, so just like before, there's an m in every term. The r squared cancels out, and 1/2 times 2/3 gives us 1/3. So we'll get GH is equal to 1/2 plus 1/3. And then we can factor out the remaining v squared. 1/2 plus 1/3 is 3/6 plus 2/6, which gives us 5/6. So if GH is 5/6 of V squared, then V is the square root of 6/5 GH.